Sir, please.
Yeah, I've started recording. Okay, good evening, everyone. So it's your first day here. So it's a demo class for fluid mechanics. Okay, so my name is Karthikeya Tiwari. Currently, I'm a PhD scholar in ISC Bangalore. I have done my BTech from SRM University and Masters and PhD in ISC. Okay, so my area of specialization is aerodynamics. Okay, and I hope all of you are for GATE Aerospace, right? Some of you may be from GATE Mechanical also. So what we are going to do here in this section, in this fluid mechanics class, which will be for around 35 hours, we will cover the common GATE syllabus for both aerospace and mechanical. Okay, and this aerospace syllabus, this portion will be taught by me. This portion, this will be your fluid mechanics, right? This portion will be taught by aerodynamics faculty, aerodynamics teacher, and this will be covered in a separate subject called as gas dynamics. Right, so this first one is basic fluid mechanics, is my section. Okay, so this section usually comes for 3 to 4 marks in your GATE aerospace exam. In GATE 2022, it was an exception. This section came for 7 marks. So you can say 3, 4, or 5 marks you can expect from this section. Okay. And for students who are going for GATE mechanical exam, this is the whole fluid mechanics and thermal sciences section. This whole section will be covered by me. Okay, in this section, whatever we are going to study in next 35 hours. So the course content has been designed like this. First of all, this part we will cover, which is the common part, in 35 hours for both GATE aerospace and mechanical, which covers the basic fluid mechanics for GATE aerospace and complete fluid mechanics for mechanical. Then there are some separate topics which are additional in GATE mechanical exam. These are the topics we will spend some additional 20 hours for this section. Okay, so this is how the course has been designed. Right, so these are the topics, these syllabus you can get in official GATE website, everywhere it is there. Right, so there is nothing new. These are some reference books which you can refer for fluid mechanics. First of all, the very, very nice book which you can refer is Sengel and Simbala. This is a story-like book. If you want to read a concept, if you want to build a concept strongly, strong foundation, you can refer this book, Sengel and Simbala. Then there is another book, Frank M. White, Fluid Mechanics by Frank M. White. It's good for concepts and numericals both. Then there is this Indian author book, Som Chakravarti and Viswas, again fluid mechanics. But this book is not good for reading. You do not want to read any concepts from here because it will have so much advanced mathematical approach. So you can refer some advanced level of numerical practice from this book. And then comes this one, K. Subramanya, 1000 Problems in Fluid Mechanics. This will be your go-to book. While after going through the lectures, if you want to solve some additional problems, this book is very good book. Right, K. Subramanya, 1000 Problems in Fluid Mechanics. The book name is only 1000 Problems in Fluid Mechanics. You will not get any concepts or anything, just some recap of a chapter, then problems, then again recap of a chapter, then problems. Okay. So if you want to solve very nice quality problems in fluid mechanics, you can go to this book. Then we have R.K. Bansal, Fluid Mechanics by R.K. Bansal. Many colleges follow this book. It's good for basic numerical practice. Apart from these reference books, where you can get your questions. See, GATE exam is all about question solving in that 3 hours, right? So your main aim is to understand the concept, then apply that concept in solving the questions. That is your aim. First of all, we have the notes which we will provide you and the questions which will be solved during the class. This will be your primary source of understanding any topic. Second, You will go to GATE PYQs, previous year questions for aerospace, for mechanical, and for engineering sciences. See, fluid mechanics is a subject which is in the syllabus of many different GATE papers. So, aerospace, mechanical, and engineering sciences, all three you can cover. If still you are remaining time, then you can go to civil previous year papers also. But I will not suggest you to go here because only these three will be enough for you: aerospace, mechanical, and XC, engineering sciences. Then third will be your test series. Whatever subjects are covered, after each subject, we will give you test series. You will give some test, some time-based test, so you can get good practice for your GATE exam. After that, we will have some assignments which will be given by IGC, right? So those assignments will be for your practice. After these four sections, if you still have some time and you need to deepen your understanding, you can go to engineering services PYQs. But please keep in mind the nature of questions in GATE exam and engineering services exam is very, very different. GATE exam is more focused on numericals. Engineering services is more focused on your conceptual understanding. Some theory based MCQs will be there. 50, 60, 70% of MCQs will be theory based. Even though numericals will be there, but those numericals will be easy because calculator is not allowed in engineering services exam. So that's why your main source of practice will be your GATE PYQs, test series, which will be given by IGC, and assignments. So after covering each subject, after covering each chapter, you should go to these GATE previous year questions, test series, and assignments for question practice. Any doubts? You can unmute, you can ask your doubts, or you can write in public chat also. Okay, nice. So I have already told you this section will be for approximately 35 hours. All the lectures will be recorded, and at the end of each lecture, you will be provided the notes of that particular lecture. Okay. Book references and numericals are optional, but I will suggest you to take this book only, K. Subramanya. See, all the concepts will be taught to you in the class only. So even after attending the class, if you have some doubts, you can ask that respective teacher of that subject. You can send them WhatsApp message. We will have WhatsApp groups also. So you will send your doubts in WhatsApp messages. Your doubts will be cleared there only. Even though after, if you want to read a concept, you think that, okay, I will read that topic from some book. So for that, I have given you these reference books, which books you can refer. Right, but please go to this K. Subramanya book. It's a very nice book for question practice. Okay. Okay, so now we will start our first chapter or first topic for fluid mechanics, which is your fluid properties, the basics of fluid mechanics. So there are some topics in this chapter which we will cover. First of all, we will see what is a fluid, definition of a fluid. Then we will see what is the difference between a fluid and a solid. Then there is something called concept of continuum. Then there are some other topics like no-slip phenomenon. Then we will start the fluid properties, different properties like density, surface tension, those kind of things, vapor pressure, these things. Then we will have Newton's law of viscosity. We will have a deeper understanding of viscosity. It's a very, very important fluid property. Then Newton gave a law for covering that part, Newton's law of viscosity. Then there is a classification of fluids, which is called as Newtonian and non-Newtonian fluids. This will be the content for this chapter, for first chapter. Okay. Okay, let us start with our first chapter of fluid mechanics. So first of all, we are going to study fluid mechanics. Okay. So all of you guys are either BTech students or you have passed out from your BTech degrees, right? So you understand both of these words, fluid and mechanics, correct? In class 11th, when we are introduced with this topic called mechanics, we are given a very, very nice definition. Mechanics means study of a system. And for our case, our system will be fluid. Study of a system at rest or motion, right? This is the very basic definition of the word mechanics, the definition of mechanics which we study. Then this mechanics is associated with the word fluid here. What is a fluid? We will see later on what is a fluid. So if I want to put the definition of fluid mechanics, I can say that fluid mechanics, it is the science which deals with fluid. Fluid can be liquid or gases, liquids or gases in rest or motion. Right, this will be your first definition of the name fluid mechanics. So we should know what we are going to study. We are going to start fluid mechanics, and in this fluid mechanics we will have liquids and gases, and we will study how they behave in rest and in motion. Clear? Okay. So now our thinking is that, okay, so fluid is something which can flow, liquids and gases, everything. Okay, so they will be in rest, they will be in motion. How a fluid differs from a solid? That comes the first question in mind. So if you are doing BTech or you are passed out from BTech, you must have studied the very, very basics of solids in the subject called strength of materials or SOM, right? So I will give you a very, very brief difference. Let us say this is a solid block. This is a solid block. It is kept on a ground, right? Let us say it is a metallic block, solid. Now what I will do, I will apply a shear stress on the top surface. This is the shear stress which I am applying, tau. Okay. So how will this solid body behave? It will deform like this, correct? And the angle will be given by phi, right? So can we understand this part? The applied shear stress and the result of the shear stress, this phi or called a shear strain, they will be directly proportional. So this tau is your shear stress. Phi is your shear strain. Stress proportional to strain. To remove the sign of proportionality, we introduce a constant G, which will be equal to tau by phi. And this G is known as modulus of rigidity or shear modulus. modulus of rigidity or shear modulus. Okay. So this is how a solid will react under a shear stress. Now, if I want to draw the stress strain diagram for this part, it will look something like this. Y-axis, let us say, is my shear stress, tau. X-axis is my shear strain, phi. So the graph will look like this. Stress is directly proportional to strain. So we will have a directly proportional means inclined line. After that, we have some necking, then ultimate stress, and then breaking point. Correct. This is the stress strain diagram we have seen already in strength of materials. In class 11th also we come across this diagram. So I can say one thing. If I have a value of shear stress tau 1.
Sir,
For that
before that,
particular,
ask some questions to them. I think they are sleeping. So make them awake and then please continue.
are you guys sleeping?
No,
It
sir.
seems like that nobody is.
No, you guys, if you have any doubts in between, you can unmute and ask me, or you can write message in public chat also.
Sir, we should not wait. They ask doubt. Before that, we should ask them doubt. Then only they will start. Yeah, please. Then.
Okay. Okay, sir. Okay. So you guys are aware with this solid mechanics part, right? Yes or no?
Yes,
You are
sir.
aware of it. Okay, so this stress strain curve, everything was, you guys are aware of this part.
Yes.
Okay, so now what I want to bring into your notice is this tau 1, one value of shear stress will give you one value of shear strain, right? If I change the value of shear stress, let us say I go to the value of tau 2, it will give me another value of shear strain. This is the case with solids, right? So we have seen this part. We have seen the relationship between stress and strain, modulus of rigidity. So I can write the shear strain is proportional to 1 by G. Okay, so which of you can tell me the definition of a rigid body? Come on. Tell me what is a rigid body. You have studied this part, right? In BTech or in class 11th also, because every time we study engineering mechanics or basic mechanics, we start with the concept of rigid body. So tell me what is a rigid body? Body which does not deform. Okay. Okay, so in this screen, you are seeing something called as modulus of rigidity. So when force is applied. Okay, nice. So can you relate this definition to this concept of modulus of rigidity? In any way, can you?
One with infinite modulus of rigidity.
Yeah, correct. Nice. So if I say that shear strain is inversely proportional to G, you are saying that in a rigid body, the body will not deform, correct? So the shear strain will be what? If the
Zero.
body will not deform, shear strain will be 0. Nice. So shear strain will be 0, or I can say that G will tend to infinity. So this case will be a case of rigid body. Right? So this was a very, very basic story of how solids will behave under a shear stress. Now our topic is fluid mechanics. We have to understand how fluids will behave. Then only we will be able to compare both of these things, right? So now let us see what will happen in the case of fluids. Again, I will take a fluid element, similar kind of fluid element I will take, and that fluid element is resting on a surface. Again, I will apply shear stress. Similar kind of element, similar kind of loading. We have to see how it will respond. See, in case of fluid, what will happen? At this shear strain will not be constant. We will get continuous values of shear strain with respect to time. Let us say at time t1, my element will look something like this. This is at time t1. And the value of shear strain, let us say we have is phi1. Okay. At time t2, the element may look something like this. So this is at time t2, and angle will become phi 2. Similarly, at time t3 also we can have something like this. So this will be your phi 3. So you can see that in this case, my shear stress is proportional to rate of shear strain phi by t. Or in differential term, if I want to write it, I can say tau proportional to d phi by dt. Earlier case, in the case of solid, we had shear stress proportional to shear strain, but here we have shear strain rate. Rate means if any quantity is changing with respect to time, it's called the rate of change. In the case of solids, we have a quantity called modulus of rigidity or shear modulus, and this quantity was introduced to remove the constant of this sign of proportionality. Right. Here also we have to remove this sign of proportionality. So I will introduce a new quantity called as mu in place of sign of proportionality. So can anybody tell me what is the name of this quantity mu?
Viscosity.
Yeah, nice. So this quantity mu is known as viscosity, or in more technical term, this is called as dynamic viscosity. Dynamic viscosity, or in questions, sometimes they refer it as normally viscosity. There's another kind of viscosity also. We will come across that part again. Right. So I can write this mu will be equal to tau divided by shear strain rate. Right. Or I can say this viscosity is inversely proportional to your shear strain rate. So I can say higher the viscosity, lesser the shear strain rate. So you guys answer one question. In one system, I have water. In another system, I have, let us say, some machine oil, lubricating oil. And I am applying the same quantity of shear stress. So which liquid will be easier to flow?
Water.
Water. Why?
Because it has lower viscosity.
Yes, viscosity is low, so this means shear strain rate will be higher, correct?
Yes.
Because viscosity is inversely proportional to shear strain rate. And the thing which we called as flow, if I say something is flowing, so this means that quantity is showing shear strain rate, correct? So if I have a solid block, let us say I have a steel block, and I have same cubical fluid element, let us say water element. So that block will show you some certain value of shear strain when applying a certain value of shear stress. If I go to the fluid part, that will show me shear strain rate. Continuously, its shape will keep on changing, and that phenomena we term it as flow. Right? So if I say anything which can flow is called a fluid, it's a very, very vague kind of definition for a layman, for a common man. If you want to explain what is a fluid, you say anything which can flow is a fluid. But in technical term, I will say anything which will show me shear strain rate will be termed as a fluid. Yes or no?
Yes.
Right? Okay, nice. So again, there is a quantity. We have seen viscosity, we have seen dynamic viscosity or viscosity, same thing. We have seen shear strain rate. There is a quantity which is called as fluidity. It is defined as inverse of your viscosity. So you can understand it with this. Higher the viscosity, lower the fluidity, lower the ability of a liquid or a fluid to flow. Lower the viscosity, higher the fluidity. Higher will be the ability of a fluid to flow. Clear? Okay, so now let us summarize whatever we have understood in this section. Let us summarize with 2-3 points. I will write 2-3 points, so please note it down with me. First point which we have studied, that what is a fluid? A fluid is a substance which is capable of flowing and what do I mean by the flowing part is flowing or deforming under the action of shear force. Deforming under the action of shear force. Shear force. Right? This was the very basic definition of fluid. Then let us see what we saw in the case of solids. In solid, the deformation is almost constant for a given stress. Is almost constant for a given value of stress. And point number 3, in fluids, the deformation changes with time. with time. So in fluids, rate of deformation is more important than deformation itself. Clear? Any doubts till now? No. Okay. So solid, liquid, solid, fluids, everything is clear, right? Now we will enter into a new topic called as no-slip phenomenon. Okay, for this, I will show you a movie. Let us say I have a plate. Correct? And my fluid is coming like this. It's a surface or a flat plate or any kind of flat surface you can assume. And my fluid is coming like this. Okay. This fluid is having some free stream velocity u infinity. Why this infinity term comes, what is free stream, we will discuss these things later, but let us understand this fluid is having some velocity u infinity. And it is also having a property called viscosity mu. Right. Now what will happen? This fluid was flowing freely earlier. Then this plate comes across in the path of the fluid. So this fluid is flowing like this lower layer has some particles. The layer which is second from the bottom is having some particles. They are moving with all of them moving with same velocity u infinity. But as they will come under the influence of the plate, the particles which are at the bottommost layer, they will attain the velocity of the plate. If the plate is at rest, so these particles will come at rest, right? So u equal to 0. Clear? This is called as no-slip phenomenon. That these particles which are near the solid body, they cannot slip on the body. So they will attain the velocity of the surface. So their velocity will become 0 if my plate is at 0. Let us take this case that velocity of plate, let us say up is 0. So my particles which are near the plate will also attain the velocity 0. Now what will happen to the particles which are at the top layers? So let us take this layer. So the particles will come. They will try to flow over this bottom layer. But what will happen? The bottom particles or the particles of the fluid, each of the particles have some attractive forces between them. These forces are called as cohesive forces. Cohesive forces means forces of attraction between fluid particles. So each of the particle attract the particle which are surrounding it. So the fluid particle which are at the top, they will try to flow with velocity u infinity, but the bottom particles are at rest. So these particles will pull them towards the plate a little bit, right? So they will decrease their velocity. So this bottom layer is at 0. This top layer will be at a little bit more than 0. It will have some velocity, but a little bit more than 0. Similar case, if we go even top, these particles will also experience an attraction force, a cohesive force. Similar case with the other particles. Understood? So these particles will make a layer like this. Can you tell me what is the name of this layer?
Boundary layer.
Yeah, nice. This is called as boundary layer. So this is how a boundary layer is formed over a surface. Clear? Any doubts regarding this part? Any doubts? Okay, nice. So now let me just take some space here. I will take a section. Let us take this location. Okay. In this location, if I want to make the velocity profile, so what does your velocity profile tells you? At what, so if I make the coordinate system, let us say this is X direction and vertically we have Y direction. So if I move from the from Y equal to 0, this means from plate, if I move towards the boundary layer in the positive Y direction, how the velocity of the fluid particles is changing. So near the plate, the velocity is 0, correct? A little bit further from the plate, we have some velocity. A little bit further, we have more velocity, then velocity is increasing, right? Because the influence of plate is weakening as we are moving farther away from the plate, correct? So this is how the velocity will be shown. This is called as your velocity profile. Clear? So near the boundary layer, so this boundary layer is the region under which the influence of the solid body is felt by the fluid particles. Outside of the boundary layer, my fluid is moving with the same free stream velocity u infinity. So what will happen if I draw this? Okay. If I draw this here, at the edge of the boundary layer, we will have velocity which will be almost equal to free stream velocity. Let us say 99% of u infinity. And just after the edge of the boundary layer, this velocity will be u infinity. Correct? Right?
Yes, sir.
Okay. So you understand how the velocity is changing, how the boundary layer is affecting the flow, how boundary layer is affecting the properties. So why this velocity profile is being formed? Why this velocity change is there between the particles? How did this whole story start?
Viscosity.
Viscosity, correct. So this whole thing is due to viscosity. So what if I say, let us take an ideal fluid which has no viscosity. So will it have a boundary layer? Think. Will it have a boundary layer or not if there is no viscosity? Will it have a velocity profile? No. Okay. So if I want to make, let us say this is a surface. Okay, again, this is a plate. And my fluid is coming like this with some velocity u infinity. And it is inviscid, means no viscosity. Inviscid flow. Viscosity is 0. So can you tell me will how the velocity profile will be there in the top of the plate? Will it be like the earlier case?
No, it
Or
will be U infinity.
it will be u infinity, right? So the fluid will behave in the similar fashion. Correct? Okay, nice. So this means you have understood how viscosity plays here. Okay, nice. Then our third basic topic before we start various fluid properties is your concept of continuum. Okay, so how many of you guys have heard this word continuum? You have some idea about what is continuum? You can unmute yourself and tell me if you know what is continuum, if you know anything about it.
The concept where space and time is said to be continuous.
Space and time. Okay. Anyone else? Continuum forces. What do you mean by continuum forces? You have studied thermodynamics in your BTech? There you come across something called, in first class of thermodynamics obviously, macroscopic and microscopic point of views. You have heard these words before?
Yes.
So do you know the difference between these things, macroscopic and microscopic?
Macroscopic is on this on the system level, and microscopic is more on the elemental or particle level.
Okay. See, there is a word which I will use again and again, fluid particle. Right. Then there are words which are called as fluid molecules. So this fluid particle, please do not understand it as a single fluid molecule. Right. So this is comprised of many molecules, but it is the smallest, you can say smallest size of the system, which we can assume in our studies, where we can have some average values of all the quantities. Like this is your macroscopic point of view. But if you go to each molecule by molecule, this will become your microscopic point of view. Okay. So this concept of continuum is nothing but your macroscopic point of view in fluid mechanics. We assume the fluid mass to be a continuous mass. We are not visiting each molecules, and we are not studying each molecule property changes one by one. Okay, we are assuming my fluid particle, fluid mass to be a continuous mass, and whatever property changes will be there. Their changes may be in the velocity, maybe in temperature, pressure, everything. So there will be those property changes will be on that complete fluid mass. How do we understand? How do we quantify this concept of continuum? Is with the help of two quantities. One is called as characteristic length or characteristic dimension, which is denoted by this LC. Another is called as mean free path. Mean free path, which is denoted by lambda. There is a relationship between these two quantities, and we define the concept of continuum based on these two quantities. Okay, so now what is mean free path? If you have studied kinetic theory of gases, this lambda is defined as average distance which a fluid particle has traveled since its last collision. Okay, so how to understand this part? Let us say I have two systems here. This is one system. So this system in terms of fluid mechanics is called as control volume, CV. Let us say this is CV1, and we have another system which is called as CV2. Okay. Each of these control volumes have their dimensions. These dimensions which affect the most in a system are called as characteristic dimension, LC1. And let us say these are the sides of these cubes or squares, whatever it is, LC1 and LC2. Okay. So in the first case, we have some fluid particles. You can assume these to be two separate rooms of different sizes. In the first room, we have, let us say, 3 particles. Okay. In the second room, we have some good number of, let us say, 10 to 12 particles here. Nice. So now what will happen? When fluid particles are inside a closed boundary, they collide with each other. Right? Like this. They will collide with each other. Here also, let us say this particle hits this one, it will hit this one, it will hit this one, it will hit this one, like this. These collisions will happen. Right? So just tell me one thing. In first container, this particle is traveling some distance before the collision. Let us say that distance is lambda 1. In second case, the number of particles is very closely packed. The number of particles is more. Here also, the particles are traveling some distance before colliding with another particle. and that distance is called as lambda 2. So tell me which will be more, lambda 1 or lambda 2? And I'm also giving you one thing, that density. If I take the density of first and density of second, I will give you that second has more density of particles than the first. So tell me, lambda 1 and lambda 2, which will be more?
Lambda 1.
Lambda 1 will be more, right? Because the density is less. Or you can say in terms of density, how the density is less? The space is more compared to the number of particles. Correct. So I can say that lambda 1 will be more than lambda 2. So this lambda is actually your mean free path. How much distance a particle is traveling before the collision. Now you tell me one thing. Which of these systems 1 and 2 is looking like more continuous mass compared to the other? System 1 has 3 particles, they are far away. System 2 has closely packed particles. Which can be assumed as more continuous mass?
Second one.
Second one, right? So if I want to see which of these systems can be studied as a microscopic point of view, and in which system I have to go and study each particle separately, I think second system will be come under the topic of continuum. First system will become under the topic of rarefied gas theory, or you can say where the particles are very rare. There are less number of particles. This cannot be assumed as a continuous mass, right? So the continuum concept is explained with this curve. This y-axis is your density, x-axis is your volume of the substance. So if the volume of substance is very, very less, so this dV is the volume above which I can assume my system to be continuous. Here your characteristic length will be very, very more than your mean free path. And in this zone where the volume is very less, or you can say the mean free path is more than your characteristic dimension, here your rarefied gas theory or the rarefied microscopic point of view studies will be more preferred. These things will be again visited in thermodynamics. This is in this zone your continuum is applicable. So in the case of fluid mechanics, which we will cover, I will give you one final point in FM or fluid mechanics. Continuum is applicable everywhere. So you do not need to worry about what each particle, how each particle or how each molecule is behaving. You can take a simple mass or simple control volume and you can start your analysis. In fluid mechanics, in thermodynamics also. In thermodynamics, in our syllabus, in GATE syllabus, only the continuum part is there. Rarefied gas theory, these things are not taught in BTech level, basically. Okay, so whatever properties we will study, like density or pressure, temperature, those properties will be defined for whole control volume of the fluid, right? I will not say that at this point in the fluid we have temperature this, at this point we have temperature this. There can be temperature gradients due to some external factors, but if I am giving you a single temperature value or single pressure value, you can assume that okay, this is for the whole control volume. Clear? Any doubts? because after this we have to start fluid properties. You can unmute, ask, or you can write in public chat. Any doubts? So let us start fluid properties. First property is the very basic property which we have been studying since class 7th, 8th or so. Mass density or density. Simply called it as density. It is denoted with this symbol rho. Okay, so how it is defined? Rho is defined as mass per unit volume, and it has units of kg per meter cube. Okay, so this V with horizontal strike, I will write this as volume, because in some places I will write use V as velocity also. So velocity will be simple V, and for volume we will have V with a horizontal strike. Okay. Okay, so I will give you a few values here. Can you tell me the density of water? You guys know density of water, right? It's a very standard value. 1000 watt. Always tell your answers with proper units. Otherwise, in GATE exam, this will create some problems. Always keep in mind right units whenever you are answering something. So the density of water is 1000 kg per meter cube, correct? But this density value is actually at 4 degrees Celsius temperature, 1 atmosphere pressure, which is your normal atmospheric pressure, and you will get water density of water rho W as 1000 kg per meter cube. Now I will do one thing. I will increase the temperature to 20 degrees Celsius and keep pressure as same, 1 atmosphere. Tell me what will happen to density. Will it increase or decrease? I have increased the temperature. Pressure is same. Tell me what will happen to density. Will it increase or decrease?
It will decrease.
It will decrease, right? So at this case, we have density close to 998 kg per meter cube. Now I am doing one thing. Keeping temperature as same, 20 degrees Celsius, I am increasing the pressure, 100 atmosphere. Now what will happen to density?
It will increase.
It will increase, right? So the value comes close to 1007 kg per meter cube. Right? So can you calculate how much density has increased when my pressure has increased 100 times? In terms of percentage, how much percentage increase we are seeing here? Can you calculate this quickly? From 998 to 1007, the difference is 9 kg per meter cube. So 9 divided by 998 into 100. What will be the percentage? quickly do this. It's not a very difficult calculation. 0.9. Okay, nice. So we will see 0.9% increase in density when pressure has increased 100 times. So what do you say? Is this change in density significant or not? Can we do, should we consider this much change or can we neglect this part? 0.9%. And we are talking about water here. We should consider 0.9%. Okay. See, anything, if change in density is less than 5%, you can ignore. Okay. So that's what I want to tell you. So in cases of liquids, you can see that if the pressure is changing 100 times, density is only increasing 0.9% in case of liquid water. So that's why liquids are always treated as incompressible fluids. You cannot change the density of the liquid. Okay, so write one note. In liquids, changes in density with respect to pressure are negligible. Therefore, liquids are treated as incompressible fluids. Okay. Liquids, incompressible fluids. Clear? And also we have talked about water. So let me just give you one value. You should remember this part. At 20 degrees Celsius and at 1 atmosphere, your atmospheric pressure, the density of air is close to 1.23 kg per meter cube. So you should remember this. It can be used in many numericals. Okay. And for water, you can remember this value, 1000 kg per meter cube. Because it is not changing much. Density is not changing much. Liquid are incompressible. So just remember this one value, 1000 kg per meter cube. Wherever you will require the density of water, just put 1000 kg per meter cube. Okay, no need to remember 998, 1007 and those things. Clear? Okay.